All right, okay, so let's get started. So as a reminder, last time we started to look at the probability, right? How do we think about uncertain resources such as wind and solar, not in a deterministic way, but in a probabilistic way? Okay, so this class we will continue to look at different distributions, how to compute statistics, and things like that. Okay, so at a basic level, where probability is, you can think of it just a sort of characterization of how often different events happen. Right? So if you look at this sort of diagram, this sort of, we have histogram, then this histogram basically tells us, if you go out and measure different things, then when you measure different things, different events occurs at different frequencies. Right? So for example, if you look at this diagram, then when power being 0 at this point, now this happened 400 times. And if you look at something like when power being 3, this happened 800 times. Right? So some events occurs more often than others, and we want to think about them in a probabilistic way. Okay, so that's the idea with probability. And we'll start off by thinking of discrete distributions. So discrete distribution means the value, the outcome of a probability, outcome of of discrete value. Right? So this is coin flip, right? So there are only two possibilities, is either head or tails, and we assign a probability to each outcome. Right? And then, so to be discrete, basically there has to be a finite number of values. Right? A finite number of values that it can take, finite number of finite number of different things that can occur. And to each of these possibilities, each of these outcomes, you assign a number. Okay? You assign a number that says how often this thing can happen. Okay, right? So there's and all this number, interpret this number as a probability. So they have to be all positive, sum up to 1. Right? And we'll think of wind to the first approximation. We'll think of wind, either wind speed or wind power, as being discretely valued. Okay, we'll assume wind can only take a discrete number of values. Okay, so to make things easier to think about when we first start. And last time we ended by looking at something called random variable. Okay, we ended by looking at something called a random variable. Random variable is not a good name, it turns out. A random variable is not a very good name. A random variable, somebody who takes probability will know that it's neither random or a variable. Okay, so random variable is basically, so what's a random variable? This is a function that assigns an outcome to a real number. So this is what random variable is. It takes some outcome and assigns a number to it, right? So in wind, the way we think about this, in wind we think about this random variable is basically so this is some process. There's actually a lot of things going on there, right? So there's basically the atmosphere. So you can think of things as pressure, temperature, other atmosphere conditions, all that through a complicated physical process. Through a complicated physical process, we can get something like wind speed. Okay? right? So it's quite, you can do a very realist model, and perhaps you can compute, one speed in first principles, right? So, but the way we're going to think of this as some random outcome. Okay, so the weather is whatever the weather is today. Depends on all, what each individual air molecule is doing. Right? So there's some complicated process. We're going to think of this as randomness. I think of this as a random outcome. Then this turns out to give us some wind speed. So this is the real number. Okay, the real number, wind speed is some real number we can think about. So for us, we'll think of wind power or wind speed as random variables because we want to add and subtract them. Okay, we want to add, subtract them, want to do algebra on them. So we have some underlying physical process, right? That's result in us observing the wind has certain speed. That is complicated. We're going to think of that as a random. Okay, there's some random things going on there. And this random process gives us a particular wind speed or wind power. So that's our random variable we're going to think about. Okay, so when we think, we're going to think of wind speed or power. Right, so this is random and has a numerical value. Okay. And this basically allows us to do addition, subtraction. We can take, for example, the cubic of the speed to get the power. Right? So we can do all these things. Right? This is because, for each of the, we'll assign a number to it. Okay, we'll assign a number to the outcome, to some random outcome. Okay, so it's important to have this number. Right? And this is actually, so we use a real number because that makes the problem easier. If you don't assign things to a number, actually it's sort of harder to understand. Okay, right? So if you go to, for example, if you go to the doctor's office, right, you have an operation, and the doctor says, okay, this operation is 80% successful. Right? I believe the probability is 80% successful. That's a probability, right? There's two possible outcomes, but then it's very hard to assign a number to it. Okay, so many things in life, when we think about probability, there's no number associated with it. But it turns out, for many engineering applications, and especially for wind and solar, we can assign a number to it, right? There's the value makes sense. Okay, the value makes engineering sense. Okay, so that's the idea we have. So here, when we look at probability, we're looking at quite at a class of probability distributions where it's actually a random variable, meaning that the outcome has a numerical value associated. There's a number associated with it. Then to be a little bit more concrete, what we have is, then we're going to think of a discrete distribution. By discrete distribution, what we have is, that means the discrete distribution means there's two vectors associated with the distribution. Okay, so when we say a discrete distribution, it consists of two vectors. In one vector, I have the probability. Okay, so let's say P1, P2, Pn. Okay, there's n possible outcomes. So we're going to say that each of this outcome is associated with a probability number, is associated with probability. And then another vector is associated with the value of this distribution. There's a value. So for us, I think of this as W1, W2, Wn, associated with the value. So the W's are real numbers, and the probability needs to obey a certain relationship. So to be probability, we need Pi to be larger or equal to 0, and to be positive, right? Does it make sense to talk about negative probabilities? So they need to be positive. And the summation of all these probabilities has to be 1. Okay? They have to sum out to 1. So that's a requirement. That's a requirement in the probability. Right? So when we have distribution, we have a list, 2 vectors. One vector contains the probability, how likely is something to occur. Another vector contains a value, Okay? And then the values are just numbers. Wi, no, is a real number you can think of. Right? There's no particular restrictions on the value something can take. Okay? So just some real number. Whereas the probability has to be positive, has to sum up to 1 for any of this to make sense. Any questions about discrete distribution? Okay, so if you ever read anything, in the slides or in your homework, it says a distribution means these 2 vectors together. Okay, so both the probability is important, and the value that these things can take is also important. Okay, so both of them together is one distribution. Okay, it's a single distribution. Okay. So for example, we have W1 through WK, K possibilities. Right, so there are K possible distributions for one. And one example of this distribution is, right, so for example, we can say a turbine has 3 possible, not a turbine. A site has 3 possible speeds. So if you measure the one speed, it has 3 possible ones. Then we can think of this as probability and speed. And maybe, it's 0.1/4, speed is 0. I say 1/3, the speed is 10 meters per second. Then left over, we have something like 5/12. The speed is 15 meters per second, right? So this is a possible distribution. Okay, this is a possible distribution, probability distribution. And you can, so this is obviously a simplification. It's unlikely a site can only have 3 possible speeds. But this is an example of a distribution that we can have. Okay, so maybe to some approximation, maybe we put the speed into 3 buckets, and these are the probabilities associated. Okay, any questions about this? Okay, and the distribution, the important thing to remember is the distribution contains all information. Okay, so what we mean is we say something a distribution is equivalent of giving you 2 vectors, so a probability vector and some vector that has a value associated with. This is the entire thing about a random variable, okay, about a distribution, right? So we say this is the full information description, right? So this contains all the things you ever want to know about this random variable, about this discrete distribution. Okay, so it has a probability, has a value associated with it. Right? So you get 2 vectors, and this you can go on to do whatever calculation we like. This is the full information. But if this is the full information description, right, this completely characterizes the random variable. What's the drawback about this? Right. So in practice, is it often that we get all the distribution information? right? So, some of you may have read, for example, the election, right? There's a lot of election forecasting. Or you look at COVID, there's a lot of forecasting. You almost never get the entire distribution. Very rarely do people provide a distribution to you. Okay, so that's quite rare. More often than not, you want to summarize this, right? You want to summarize this information somehow. Okay, so let's say you're working and your manager comes in, tell me something about the wind I can have tomorrow. You're not gonna say, okay, this is two vectors, each 1,000 long, each 1,000 components, and this is what will happen tomorrow, right? That's not how people often interpret this kind of randomness. So if you think about, right, the places where you have how people talk about this sort of random occurrence, random variables, the more often than not, as you often want a summary of this. Okay, so even though when we have say a distribution, that means two vectors, probability and value. When you use it or you communicate it, it's rare to give all the information, right? So quite rare to provide all the information. What's more common is to provide so-called statistics of the distribution, right? To provide a statistics of it. So a statistics is basically a summary, okay? Sort of summary of the distribution. Okay? So we're not interested in the whole vectors, no, we're not interested in getting all the numbers, then we're often interested in a summary of the statistics summary. So for the folks who's familiar with this, what are some example of statistics? So how would you summarize a distribution? So think of when you do an exam, what kind of summary is given?
Like a mean and a standard deviation?
Right, so one example, the common example we have is, for example, mean, right? What is the average value of this distribution? What is a variance or the standard deviation? What is a variance? Right? So these are the most common ones you get. Right? So when you do an exam, for example, in Canvas, you'll see, the mean of the score is this, and the standard deviation is this, right? So these are not the full statistics, right? When you look at when you go on Canvas and look at exam and look at the mean and standard deviation, you don't know the entire distribution. You don't know who got what, right? But you still figure out some useful information from it. So this is the mean and variance of this distribution. What other things are there besides mean and variance? What other possible things do we want to know? Especially in the context of wind, right? So let's say you are operating a wind farm and somebody comes in and say, oh, I forecasted for tomorrow, the mean wind power is this, the standard deviation is this. So, right, so variance is sort of similar to standard deviation, right? Just sort of the square of it. Any other things you may want to know? So the chat says peak to minimum ratio. This is close, right? So any other you may want to know other things, for example, as a quantile information, right? You may be interested in, okay, how often do I get, let's say, 90% of my capacity? Or how often do I operate about 50% of my capacity? Right? These are things like quantiles. Okay, so this, for example, this is how often is the output larger than 50% of capacity. Right? So this is maybe statistics, right? So you want to know, for wind power especially, you want to operate, the mean can be high, but if you zero a lot of time, then that may not be good. Okay, so you want to understand all these numbers. Right? So often, we're often as we don't communicate or we don't often there's too much to look at the entire distribution, right? Maybe many numbers in a vector, but often this is communicated through the statistics of the distribution. But the important thing to remember is the statistics does not give the entire picture. Okay, a statistic is simply a number computed based on this distribution. It's not the entire picture. So when you get statistics, it's very important to think about what the statistics says. Right? Think about, does the statistics give you enough information? Okay, so there's quite a bit of probabilistic thinking. There's a trade-off between how much information you have, how much information you provide, versus how much you can interpret about. Right? So statistics are easier to interpret. Mean has a very well-defined, right? So it's sort of very rigorously defined what a mean is, but it doesn't contain all that much information, right? So it's often a trade-off between, or it's often the idea you need to find the right statistics to look at, right? So the right values to look at. Okay? So as a review, most of us are probably familiar with this, right? So what is a mean? So we'll write this as mean or called average. So the reference book uses this average for mean. So we have, right? So this is just the value, right? Weighted by the probability can occur. So this is simply a weighted sum of the values. Then the variance is a weighted sum of the deviation from the mean. Right? So this is our variance. This is the deviation away from the mean. Right? Any questions about this? So I'm assuming most of you are familiar with this. Okay, so you'll be computing for sure some variance and some means, right? So okay, so this variance and mean. Then we can, for example, right, we can look at a simple example of the variance and mean. So here, let's say we have different speed, 0, 10, and 15. We have different probabilities. So the average is 1/3 times 0 plus 1/3 times 10 plus 1/3 times 15. Right? So this is our average. So you had about 8.33 meters per second. Okay, so the variance, the mean has the same unit as the wind speed, right? So this is the mean, this same unit as wind speed. So the variance denoted by sigma squared. This is, right? So the important thing to remember is you're squaring, right? You're squaring the difference between the value and the mean. So this is 1/3, 8.0 minus 8.33 squared plus 1/3, 10 minus 8.33 squared plus 1/3, 15 minus 8. Okay. So this is whatever you compute this thing out to be. Okay. All right, so this is the variance, right? So you can compute the mean and the variance and different other statistics based on this kind of distribution information, right? And again, it's important to look beyond the mean. Okay, so we, as people often has a tendency of just looking at the mean. We're focusing on more on the mean than anything else. Right, that a lot of times is probably not the best strategy, especially for something like wind. Okay, you need to look both at the mean and the other statistics that we have. All right, so any questions? Okay, so then there's special names associated with mean and variance, right? So, so the mean measures, again, the average magnitude of wind. The variance and standard deviation measures the how, spread the values are, how much spread there are. So these are called, first order and second order statistics. Okay, so a fancier name for these, the mean is called a first order statistics. The variance is called a second order statistics. The reason we use first and second order is when you compute the mean, this is pi multiplied by wi. So it's wi to the first order. You raise wi to the first order. Variance called second order is because you square it in the second equation for variance. So this is called a second order information, right? So these are, again, the most commonly used ones, right? So we have first order, second order, then maybe higher order information if we really want to, understand the distribution in more detail. Okay? But often we just give first and second order information. Okay? So again, if you get exam, right, the first and second order information are included. Right? So these are the ideas, but for second order information. So again, let's just do some examples to make sure that we're on the same page and to have a look at, things when things are not uniformly, things don't have uniform probabilities. Okay. So for example, you can have so before we have probability that's all 1/3. But that doesn't have to be the case. So the probability can be any value as long as they are between 0 and 1 and they add up to 1. Okay, as long as that happens, then it's fine. Okay, so there's no other restrictions on the probability values. So let's look at two wind farms. So wind farm 1, let's say we have 3 possible speeds. Wind farm 2, let's say we have 2 possible speeds, 4 possible speeds. And then I compute the mean and variance of all these. So again, these are fairly easy calculations, right? So for wind farm 1, the average is the probability multiplied by the value. So our probability is 0.3 times 0, 0.5 times 5, 0.2 times 10. You add it all up, we get 4.5 meters per second. Then if you look at the standard deviation, we have 0.3, 4.5, squared, 0.5, 5 minus 4.5 squared, 0.2, 10 minus squared. So this is the standard deviation. Okay. Sorry, this is a variance. This is a variance. So the variance, because we're squaring, has a unit that is squared. Okay, so the unit of the variance, this is actually meters squared per second squared, right? Because we're squaring all these numbers. So this unit is not, something that easily we can interpret. So the standard deviation is just a square root of the thing. And then if you take a square root, this gives us an idea of 3.5 meters per second. So the mean is 4.5, the standard deviation 3.5. So this has a fairly large spread. This has a fairly large spread. All right, then we can look at something like, so for farm 2, the exact same calculations, we get the average is 4.4 meters per second, and the standard deviation is 3.14 meters per second. So these are sort of quite simple calculations we can do.
Just have a
And
quick question
yeah,
for
go ahead.
farm one wind one average. You say zero point 0.3 times zero. How do you get zero?
Oh, the speed is 0.
Or what do you say?
The speed is 0, right? So there are 3 possible speed. The first possible speed is 0 meters per second,
Oh, okay. And then 0.5 times 5.
right? So for the second speed, the probability is 0.5.
Okay.
For the third speed, 10 meters per second, the probability is 0.2.
Oh, okay. Okay. Got it now. I got it. Thank you. I got it.
Okay, all right. Other questions about this? So you'll be doing this a lot, actually, in the homework and in the midterm, right? Since this time for exams, you can use computers, so I can give fairly long vectors, right? So as you probably see a question that has maybe 20 possible speeds, and they all have different probabilities. I can do this type of calculation. Okay, so be prepared with those kind of questions. Okay, so probability, right? So for now, for us, we're looking at a very, very simple probabilities, right? There's probability that can lead to a lot of interesting phenomena, right? You may not think of, but in this class, we'll stick with this sort of very simple things. We'll compute, some mean, some standard deviation. We'll compute something like, the chance of the wind is above a certain threshold, things like that. Okay, so we'll compute those kind of probabilities. Okay. So this is right. So this is, for example, this type of question is, you're given we have a distribution, right? In this case, we have a distribution. We know what are the probabilities. We know the probabilities at which certain speeds occur. So then that's just straightforward calculation. But in practice, we never know the probability distribution. Right? So you go out and look in practice. Let's say you saw a turbine somewhere, and you ask, okay, now please give me a list. Give me the entire distribution information. Nobody has it, right? We don't know what the probability is. Right? There's no way we know what the probability is. So we often need to resort to something called empirical probability. Empirical probability is simply a fancy name. It's a fancy name to say we don't know what the probability is, so we're going to measure it. Okay, so that's just what that means, right? So this is we're going to build a distribution based on measurements. Okay, we're going to build this distribution based on the measurements we collect, right? Because in practice, it's almost impossible to get the true distribution. Okay? If you look at any wind turbine, you say, okay, what is the distribution of your wind power production? Can you give me an equation that describes it? That's almost never the case, right? Most of the times we need to do some measurement. So the typical way we do measurement is the following. So we go to, let's say, a turbine or a site at our T. We measure WT. Okay, we measure the speed. Okay, we take some measurement and we measure the speed. And then after n hours, we have n measurements, right? Because at each hour I take a measurement, maybe the average speed of the average speed I see within this hour. Okay, I take n measurement. Right? So I do this n times or n hours. There's capital N measurements I have. Then what's the next step? If I'm building this empirical probability. So I go out there, let's say I look at, over a year, So that's 8,760 hours. I take 8,760 measurements. Then what do I do after that? Do I just say each of these measurements have a chance of 1/n happening? Is that the best practice? Right? If you think about it, right, well, if you measure the speed of wind, every hour you get a different speed. It's a real number. So there's no 2 hours the speed will be exactly the same. That's with probability 0. Right? Will speed be the same? So after this measurements, after n measurements, you'll get probably very high probability n distinct numbers. Then how do you build a distribution on this? Do you just take this n numbers and say, okay, each of them happened exactly once? So each of them has probability 1/n happening?
You could group them into a range and then like see how many of the total number of measurements fall into that range.
Right. So the standard practice is to group them into a range, or this is called a bin it. Right? We have to bin these measurements. Because if you don't bin it, it's not all that useful. Right? So each of them occur once. That's not a terribly useful information. So what we do is we bin it. Right? So it's almost binning. So that's why also one can be thought as a discrete phenomenon. Because if we go out there and we measure real numbers, real values, or values that are real numbers, still we have to bin it for it to be more useful. So after that, we bin the measurements. Okay, we bin the measurements. So this, for example, WT from 9.5 to 10.5 are assigned to 10 meters per second. Okay. So we're gonna bin it, right? We're gonna count how many samples falls inside this range. Okay. So then we have K bins, each with n sub I measurements. Okay. So each with n sub measurements. So this is how we talk about the probability, right? So we're gonna think of this, we have after binning, or let's call this n sub I samples. Okay. So we have n1, n to the capital K, and then what we have is then we know that n1 plus n capital nk equals to capital N, right? So each of them has to each measurement has to go to one of the bins. So in total, the number of total samples we have equals the total measurements we made. Okay, so this is the idea. So this is how we empirically construct the distribution. Okay, do measurement, do a binning, and then count the number of measurement that falls into each of the bins. So we can bin this in many ways. Okay, there's not a sort of the best way or into binning. There are different applications, may have different things. So may have different requirements for how you bin. So we're gonna basically, for this class, we're gonna think about sort of this equal width bins. Okay, so it's most easier to think about bins of equal width, right? And this is, again, repeating the picture we had before. This is if you go out there and you measure the speed and you put them onto a bin. Okay, that's just what the distribution will look like. Okay. So if you bin them, basically what we get is we get a frequency count. Right? So we bin them. So remember, we have K bins. Each of them has a number of samples associated with it. So these are called the frequency count. Okay, this is called the frequency count. Right, so this is not a probability. It's not a probability yet because they're not 1, right? They don't add up to 1. They're not a number between 0 and 1. So to convert it to a probability, it's quite easy. We simply define PI as the number of samples in my bin over the total number of samples I have. Okay, so this is quite simple. Right? Then of course I have the summation equal to 1, right? So PI is for sure positive and between 0 and 1, and the summation is 1 because I have that many total samples. Right, so that's just the probability of constructing probability from these frequency measurements. Okay, so any questions about this? Okay, so we can do this. Then what we get is, so before, remember, we have this histogram. This is, counts. This is frequency count. You divide by the total number of samples, you get probability, right? So on the y-axis, now we're plotting probability because these are now normalized. You can think of between 0 and 1. So this is probability. So again, all fairly straightforward, quite simple for us. Okay. So then you can compute the average very easily, exactly as before. Right. So this is again the probability multiplied by the value. You have total. Right. So you have the number, you have the values, and you have the counts or the probability associated with each value. Right. So this is our average speed, exact same equation. And then variance and standard deviation also the exact same equation as before. Okay, so there's no change with this. Okay, so if you want, you can put the n inside and write variance this way: pi wi minus w average squared, where pi is small n I, so number of samples in the bin over the total number of samples. And standard deviation is, of course, taking a square root of this thing. Right, so that's the idea we have. Okay, so that's the variance and deviation. Okay, so any questions about this?
Sorry, what is the difference between omega I and omega average?
So average is the average value computed this way. Right, W average is the average of one speed. Mm-hmm. Wi is the one speed I get from each of the bins. So for example, these are the Wi's, right? The possible speed may be 0.5, 1.5, and so on. And then from all of them, I can compute an average.
Okay.
Right, so if you look at before, the example we did is, okay, so let's look at this example, right? My Wi's are 0, 5, and 10. Right, so there are 3 possibilities.
Yeah.
3 values. Each of them has probability 0.3, 0.5, 0.2. Right. Then the average is just this weighted sum. So that's the average speed.
Okay, thank you.
Yeah, so that's the average speed. Yeah. Okay, good. Yeah, so yeah, if you have any question, please ask. You'll see this quite a bit, right? So all these problems are actually fairly simple to do, but you want to make sure you understand the definitions correctly. Okay, any other questions about these equations?
Quick question: the standard deviation is just the positive root, or?
Yes. So right. So the square root symbol means the positive root. Yes.
Okay. Thanks.
Any other questions? Okay, so something to think about is, right, so something to think about something called estimators, right? So if you look at these equations, the variance or the mean calculation. So we have an empirical probability, right? We have some empirical probability, empirical distribution. We compute a average speed, right? So the way it works is, right? So there is some distribution. So we don't know, right? We don't know this distribution. Okay, so we're going to sample. Then we're going to construct things like, Wi. So sample n times. When we bin it, we get Ni and Wi, right? We construct this for samples. These are the samples we have, okay? So there's some distribution that we don't know, but let's give it a name, right? Let's give this distribution, let's say D. Okay, so let's call this distribution D. So there's two ways to compute it, right? So one is I can find the average from D. Okay, so let's call this some W average. Right, so this is some W average. Or I can find the average this way. I can find the average, call this hat. Okay, so I can go to my measurement. I can go to my measurement and find another value, W hat, right? W average hat, the estimated value. Okay. Then what is the relationship between how is W average related to W hat? Okay, so W average is a true mean, right? It's saying suppose I know the distribution, I can compute the mean. So the distribution itself, right? You go to some site, there is some true mean speed of the wind. Okay, right? So if you know everything, if you know how air molecule move and things like that, you can compute this true mean. Right? We cannot do that. So we go and we compute the sample average. Right? We take samples, we bin them, then we take an average. Okay, then we take sort of find the average speed. So how are they related? How are they actually related to each other? Right, so is W average hat a good estimate? Right, so somebody tell you, hey, I went to the site, I took some measurements, I compute this average. How confident should you be about this average? Right, so you build a wind turbine. Let's say you're building some wind turbine somewhere, and you can only make money if, let's say the mean wind speed is above 15 meters per second. Okay, so you did some calculation, you figure out that's the way you make money. Right? Then I said, oh yeah, I went to that place yesterday. I measured, 5 times. I guess the average is 20 meters per second. You're probably fine. Right? So should you trust that? Right, so how is the sample related to the true mean? How is the measure, right? So I can measure, I guess, some estimate of the mean. How does my estimate relate to the sort of the ground truth mean? Any ideas?
Is it that if you take more samples, you'll get closer to the true mean?
Right, so as you take more samples, you get closer, right? So that's to be expected, right? So they relate basically in the following way. So as n goes to infinity, as you take more and more samples, your estimator goes to, right? So your estimator goes to the true value. Okay, so even though you don't know what the true value is, you're becoming more and more confident that your estimator will go to the true value. Okay, so this is called a consistent estimator, right? This is called a consistent estimator because so as the more measurement you take, the closer you are. So this is, in some sense, this is either, this is a law of large numbers. Right? This, we take in probability, this is a law of large numbers. There's sort of different types of law of large numbers, but they all say that as you take more and more measurement and you sample more and more often, you converge to the true thing you want, the true value, the ground truth value. And how this converges, right? So how many is enough measurements is actually complicated. A lot of probability theory, a lot of statistics is precisely about how often do I have to measure, right? What to do when I don't have enough measurement, right? It's about this kind of things, right? So how do you think about that? So if you take for example, if you take probability from a math department, right? Take sort of math probability, it takes you a semester or a quarter to basically prove this. This is actually not all that trivial of a proof. Right? So in our mind, we think, of course, as you sample more and more often, you should recover the true value. To actually rigorously do this is not that straightforward. It takes some effort actually to do this kind of proof, why this convergence happens. And this convergence can happen in many different ways. Right? So for this class, we'll take we'll often, or if not always, think of the measured mean, the sort of the estimated statistics and the true statistics as the same thing. But that's in your mind, you should be able to make a distinction, right? So if you go out and work, often you would be dealing with small sample size when the capital N is not all that large. And then it's important to be aware you're only dealing with estimator, right? Not the true value, not the ground truth, but only estimator. So that's something to keep in mind, right? But when we do calculations, more often than not, we'll just pretend the estimated probability is the true probability and go from there. Okay? So that's how we do it. If you're interested more, this kind of things, there's a lot of class from the stats department, for example, to take to sort of really think about how does the empirical process collecting samples relate to the true underlying process that's happening. Okay. Right. So now let's take. Okay. So this is a good place for a break. So let's break for 10 minutes. We'll come back at 1:35. We'll resume at 1:35. Okay, all right, so let's get started again. Right, so the first half of the class, what we've been talking about mostly is computing something like a mean or the average or the standard deviation, something like that, right? But also given the distribution, we can compute things like probabilities. Right? So for probabilities, what I mean is the following. Let's again say we have values. Now we have one speed, one WK was probably P1, PK. Okay. We can ask a question like, what is the probability that the wind is between, say, 5 meters per second to 20 meters per second? Okay. So we can ask this type of questions, right? We may be interested in the fraction of time that the wind happens in this range. Okay, so this is another thing potentially of interest. And this, again, this for computation is quite simple, right? Quite simple. All we need to do is just add up, right? We just need to add up the probability of the values that occur within this range. All right, so for example, let's say we have the speed, that's the meters per second, going from 0, say 4, 6, 10, 15, 21. And the probability, say this is 0.1, 0.2, 0.1, 0.3, 0.2. Okay, so let's say this is the data we're given, and we're interested in the probability that if I operate this, I'll see a speed between 5 and 20. Okay, then the probability that the speed is within range, we simply go look at which are the values that falls between 5 and 20 as these three. Then we add up the probabilities here. Okay, we add up, so this is 0.1 plus 0.1 plus 0.3, 0.5, right? So we know that 50% of the time, we can expect the 50% of the time, the speed will be between these two endpoints. Right? So this is another thing that may be of interest to us, right? So we're interested, for example, the mean, but we also want to know when there's a speed not too low and not too high, right? So we can compute this kind of probability. Okay? And they all give different informations, right? So they all give different informations. So we can look at, right? So we normally are interested in a bunch of statistics, right? This kind of probability is one of them. Right? Any questions with the example? Questions with the example? Okay. So more formally, we can define something called the cumulative distribution function. Okay, so all this is just a fancy name for the total probability. Okay, it's just a fancy name. Basically, what it says is, if we're interested in the probability between these two ranges, WA and WB, what you do is you sum up the probability of the values that fall inside these two ranges. Okay, right? You just sum these probabilities up, okay? And you get a number between 0 and 1, and that's a probability. Right? And we invent a name for this, and this is called the cumulative distribution function. It's a fancy name for a function summarizing the probability of something happening. Okay? Or this is just a fancy name. Okay, any questions about this? Okay, so one thing to note is that this function, the dependence on the value is such that if the value falls in within the range, then the exact number doesn't matter, right? So if you look at this, for example, we have 0, 4, 6, 10, 15, 20, 21. Okay? So 6, 10, 15 falls under this range. Right? I got a probability of 0.5. So if, for example, this number 10 changed to 11, will not impact the probability. Okay? So be a little bit careful of the dependence on value. Right? So the value just determines whether it's in the range or not.
200.
Yeah. Questions?
خليفتي شلل. Oh yeah. سرة خسرك.
Okay, so I'm gonna mute.
Huh?
All right. Okay, all right. So, okay, any other questions? Okay, so that's the CDF. That's the sort of this is cumulative distribution function, very often written as something called a CDF. Okay, that's CDF. Okay, so for a discrete random variable, CDF is not too difficult to calculate, just add up the values. And so far we have been talking about the wind as a discrete random variable, right? That's a discrete thing. Okay, so for a discrete random variable has a good, is easy to measure, easy to sample, right? You can sample, you can bin, you can have this sort of empirical distribution. So that's a good thing about it. Anybody see some drawbacks with a discrete random variable? Right? Are there any drawbacks you can see? Right? Is it do you see some disadvantages of giving lots of numbers, right? Lots of probability, lots of values. Right. So one big drawback about discrete random variable is this. And so again, if you look at a histogram like this thing, okay, there is a lot of values to give, right? So remember, to characterize this as a vector, I need two vectors. A vector of probability and a vector of the values, right? The realization, the possible realizations. Okay. So that sometimes can be a lot of information. Okay, there's no easy way to summarize this, right? There's no easy way to, you can summarize this by computing statistics, but the statistics does not give you the full information, right? You can compute the mean out of this, but knowing the mean does not give you the full distribution, right? Just telling the mean, you don't know what this whole distribution is. But to tell you the entire distribution, I need to give you a lot of numbers. I need to give you too big vector of numbers, which is hard to do. Okay, so the discrete distribution, yes, you can measure it, right? So empirically you can measure it. To a computer, it's probably fairly easy to handle. A computer can handle this very easily. But to us, to engineers, sometimes just hard to think about this, right? Because if it's parameterized by the mean doesn't give us the full information. Okay? But to get the full information, too many numbers, right, to deal with. So one way to overcome this is to think about continuous distributions. Okay, so instead of thinking about discrete things, we can think about things that are continuous. Right? We can think about things that can take values, not just some finite, not can just have finite values, but take number values over the real lot. Okay, so that's our continuous distribution. Okay. And this is something called the PDF. The meaning of PDF will become clear later, but let's think something called PDF. Okay. So what this does is convenient, a lot of this for convenience, to model wind or solar or any sort of these things with a continuous distribution. Okay. Turns out it's to model with a continuous one. So a continuous distribution basically means that there is a function called the PDF, the probability density function. Okay, that takes a value, let's say this is wind speed, and assigns it to this function f of w. Okay, assigns this to a function f of w. This is what you can think of a density as. Okay, so for example, I can have, for f of the wind being 15 meters per second, right? This is right? So this is possible. Right? I can take, say, what is the probability density of the value of wind being 15 meters per second. Okay, this is called the PDF. Right? So the PDF turns out, so the PDF is, this has to be bigger or equal to 0. Okay, there's still in some sense a probability, right? Some sense of probability, so it has to be positive, it cannot be negative. We don't know how to think about it being negative. Okay. But the idea is to say the integral now from -infinity to infinity is 1. Okay, so instead of thinking, when you have discrete numbers, each of them, right? When you have discrete numbers, each of them being between 0 and 1 and summing up to 1. Turns out to the PDF for the continuous versions, we just need the function, the PDF function, to be positive, and the integral to be 1. Okay, so that's all we need for this to be a PDF. Okay, so we drop, right? So this, right? So the idea is this can be larger than 1. This can be okay. It's okay if the value is larger than 1, as long as the integral is exactly 1. Okay, so it has to be all positive. Value can be larger than 1, but the integral, can be, right? I can have the integral being, I can have the value being large, the function being higher than 1 at different points. So the way to think about this, so where does this, continuous thing come from? Where does this density function come from? The way to think about it is, if I take a CDF, I take this and squeeze it, right? I can squeeze it, where the interval I look is smaller and smaller. Okay, so if I take this limit, I essentially get the probability density function. Okay. So what I can do is the following. Okay, what I can do is this as the, basically, if you look at the probability of the value being between, so let me write this carefully. Okay, so this basically, you're saying, what is the probability of living in this very small interval, weighted or normalized by the length of this interval? And if you let this thing approach 0, you basically get, by definition, the PDF, okay, the density function. So it's looking at as a probability, except the probability is weighted. Okay, the probability is normalized by this interval you're looking at. So you take a discrete distribution, you squeeze it, basically, as you keep squeezing it, and then you get a density. And this you can think of as a derivative of the probability. Okay, this is essentially a derivative. Right? You look at this formula, it's basically we're taking a derivative. Right? So it's a derivative of the probability, the cumulative probability function, you get the density. Okay. And because for a continuous value function, we have to think about the density. because W can take on any value. It's a real number, right? So we must assign each real number a value. So that's the f of W. That's the PDF, okay, the density function. Any question about this? Question of PDF? Right, so we'll only use a few kinds of PDF, but I want you guys to get into a feeling what this is. This is basically, you can think of, I take a cumulative distribution function and discrete. I take a discrete probability and discretize it or quantize it as finely as possible. Right, you do a very fine quantization, then you get this kind of PDF. So PDF, again, what you can think about it, graphically, you can think about this as smoothing out. Okay, we're gonna smooth out, right? We're gonna smooth out the distribution into a continuous function, into a curve, right? So that's a PDF. So this PDF, again, just to look at the properties, right? So an important property is, so this integral must be 1. Okay, this integral has to be 1. The function has to be always above 0, or function has to be always non-negative. And the probability as between the value taken between A and B is basically the integral, right? Is the integral under the curve. So for example, if the distribution is something like this, this is A, this is B, this is the integral under the curve is the probability of this function is the probability of the, let's say, one speed falling inside this range. Okay, this probability. All right, so this is our properties of the PDF. Okay, so this is continuous version. Okay, so why is this better than the discrete? So I mean, we spent 20 minutes on this talking about this for continuous functions. And so instead of doing sum, we're doing integral, which is often much harder than doing a sum, right? So why do we want to talk about this for continuous functions? Right. So the reason we talk about these continuous functions is often when you go to a function instead of a vector or a table of numbers, you can parameterize a function fairly easily. Okay, there's easy ways to parameterize a function, whereas parameterize a table of numbers is harder. Right. So one example of parameterizing a function is this. Okay, so one example of parameterizing function, it allows to have a uniform distribution. Okay, uniform, what it means is between A and B. So this means the function has the equal chance of happening. Any value has equal chance of happening if it's between A and B, and no chance of happening if it's outside A and B. Okay, so this is a uniform distribution I can have. Okay. So that's what this looks like, the following. Okay, so if you look at the PDF, A and B, so outside of it is definitely 0. Okay, so inside of it, it's the same value, right? It's exactly, it's all the same value. So everything has an equal chance of happening. So what is the height of this function? So how high is the function in the middle? How high is it? So outside this range A to B is definitely 0. Inside is the same chance of happening. So then what is f of W inside A and B?
The integral is equal to 1.
The integral is equal to 1, and everything has the same value. So this has to be 1 over b minus a. Right? So that's what the value this has to take, right? Because the integral is equal to 1. Right? So recall a to b f of w is equal to 1. This is a constant, right? They must have the same value, right? So then it's a constant that doesn't change. So this is 1 over b minus a. Let's say this, 0 otherwise. Right? 0 otherwise, okay? So the good thing about this kind of continuous, the PDF, the density function, is actually quite easy to describe it, right? We only require 2 numbers in the uniform case. Okay? We only require 2 numbers, the upper and the lower bound. So I can tell you this is uniform between A and B, and you know everything about it. Okay? You know the entire PDF, and you can compute everything you want from the PDF. Okay? Whereas if I want to say this for discrete, now for a discrete value, this gets harder because I'll tell you, okay, this is A and B, I'll tell you what is the bin width, right? How many bins do I have between A and B? I'll tell you number of bins. Then you have to think about, okay, does it depend on the bin size, right? Does it depend on how many bins I have? Right, so the mean, for example, will depend on the exact number of bins I have, right? So it depends. Then that becomes sort of too inconvenient, and maybe you're not binning at the same size, and all that becomes inconvenient to deal with. Whereas for a continuous PDF, sort of the form is often cleaner. Okay? For example, this one is characterized by 2 numbers. Right? Only corresponds 2 numbers. So whereas a discrete distribution is characterized by sometimes by tables of numbers, a continuous distribution is often characterized by a few parameters. And so it's easier to communicate these few parameters than to communicate these tables of numbers. Okay, so just because things are continuous does not mean it's harder. Often it's much, much easier for things to be continuous. Right, so this is one example, as you only require a few things to describe this continuous numbers, this sort of PDF. Okay? All right, and once you describe the PDF, you can compute everything you want out of it, right? So the mean, same formula as before. Sum becomes integral, and just integrate this thing. Variance, same thing, integrate the squared. Standard deviation, you take a spell standard deviation wrong. So okay, standard deviation, you take a square root of it. All right, so this is, if you know the PDF turns out to be very easy to communicate. It's parameterized by a relative few number of parameters, and you can use a small number of parameters to compute the rest of the information. Okay. Any question? All right, okay, so for this class, we're only going to care about 3 PDFs, 3 particular PDFs, because they're used in wind modeling. Using wind modeling, okay, we're going to have you talk about 3 of them. So the 3 are normal, or Gaussian, which we all heard about. Rayleigh is less often used, but also used in practice. Weibull is also used in practice, so we're going to look at this. So today we're going to look at only a normal distribution, which we have all seen. Next class, we'll look at the other 2. Okay, so the normal distribution function, I'm sure we have all seen before. Right, so this is the famous bell curve, or the distribution function. This is 1 over sigma 2 pi e to the minus w minus Let's be careful what I use. The average squared over 2 sigma squared. All right, so there's 2 parameters. The mean W average and the standard deviation. Sigma. Okay, so that's the Gaussian or a normal distribution is characterized by these 2 parameters, right? The mean and the standard deviation. So if I tell you the standard deviation, I tell you what the if I tell you those 2 numbers, I tell you what the PDF is. Okay. And again, the reason we want to use Gaussian, one reason we want to use Gaussian is I only need 2 numbers to specify the entire PDF, the full information. So if I go out and measure, for example, I use Estimator, I can measure the mean. I take a bunch of samples, I do the sample average, get the mean. I take a bunch of samples, I do the sample average, I get standard deviation. Those 2 numbers is enough to describe the entire PDF. Okay. Which is, this makes it very easy to use. Okay. Whereas compared to the discrete distribution, I need to give you the entire table or entire histogram. Here, I only give you 2 numbers and you know everything out of it. Okay. So this is why we use it. So for the shape of the distribution, again, we have all seen it. Right, this sort of bell curve, spread high in the middle, test sort of tails that falls off fairly quickly. It tails falls off quite quickly to both sides. And right, so the shape depends on both what the mean is and what the standard deviation is. So we really like to use normal distribution. We really like normal distribution because again, there's 2 parameters for us to measure. And the parameters are the parameters that make sense. The parameter that's the easiest to interpret. We know what mean, we know what average is, we know what standard deviation is. We measure these 2, and somehow this describes the entire function for us. Okay? This describes the entire function for us. Okay. Okay. Any questions? Okay. So if you look at the Gaussian or the normal distribution, it's easy to use for sure. It's easy to characterize. It only takes 2 numbers. Is this a good distribution for wind? Do you think wind actually looks like a Gaussian? Is this really good for wind? Like, will you expect you go out and measure a turbine, like you just take values and build a histogram, would it actually look like a Gaussian? Right. Right. So the problem with a Gaussian is, or a normal distribution is it's easy to use. We have a lot of formulas with Gaussians, right? With all this we have. The issue with a normal distribution is wind farm really doesn't look like this, right? If you look at the alpha, it doesn't look like this. One issue as a normal distribution goes infinitely long. The tails are infinitely long. So it goes from minus infinity or positive infinity. Okay, that's for sure does not describe what wind is, right? There's no minus, right? There's no minus power. There's no negative power generated. And of course, the power can generate is not infinity. But for a normal distribution, the tail just goes as unbounded, right? The tail goes to both sides of infinity, to both infinities. Okay, that's one reason. Okay. And second, this thing just sort of symmetric, right? This is symmetric, and in practice, the wind power or wind speed is probably not symmetric. There's no reason for it to be symmetric. Okay. So when we first started, people think about probability and looking at wind power. A lot of it was modeled with, assuming wind is normal. That can run you into some problems. Okay, assuming wind is normal can lead to some bad conclusions because wind is often not normal. Okay, it's not symmetric. It's not unbounded. It's definitely bounded on both sides. Right? It's above 0 and below capacity. That's that. And then assuming normal distribution really leads us into problems. Okay. Okay, so right, so we start using normal distribution. You know, we look at some of the early modeling with normal distribution. You know, all those calculations now you need to take a grain of salt, right? So if you look at a lot of modeling papers, you know, it's normal distribution, right? That's really not true, right? Not the way you want to think about it. Okay, so nowadays very few people use normal distribution to model wind. Okay, it's just not very often done. We don't use it. However, normal distribution is still useful we don't use it to model wind, but it's still useful. You still see it used all the time. So I said, you know, wind is not symmetric, you know, it's on both sides and things like that. Can you think of a case where normal distribution is useful? So if you look at the wind power, let's say generated by a turbine, it's definitely not a normal distribution. But are there something that's reasonably modeled by a normal distribution? You think of something, right? So normal distributions are really, really nice. Okay, we want to use them if we can. So solar is also not. Solar, for example, is bigger than 0 and capped at something.
Like weighting coal and other like gases, oils.
No, so none of this is very normal. Right? So normal distribution has an issue is symmetric, right? One other problem is symmetric. There are very few things that's symmetric. Okay. There are very few things that are symmetric except forecast error. Okay, so the one place, or actually this important place, where normal distribution is still used, this is forecast error. Okay. Because when we talk about uncertainty, often uncertainty show up in the following way. Okay, I have some wind. Okay, so let's say wind. Let's say this W is wind speed for tomorrow at what time is it? 2 p.m. Okay, let's say this is the random variable I want to look at. It's random, of course, right? But what we often do is we think about this random variable in 2 steps. One is we'll have a forecast. Okay, we'll have a forecast. Okay, we'll try to forecast what this is, right? Maybe we forecast to be 10 meters per second in this forecast. Of course, the forecast is not 100% accurate. We can, right? It's not exactly the forecast. Then we're going to plus this with the error. Okay, we're going to plus this with the error. So we're going to decompose this random thing into 2 things. The forecast is deterministic. Okay, we're going to think of the forecast as a deterministic number. For example, 10 meters per second. We're going to think of this error as random. Okay? We're going to think of the way it works is we'll do a forecast, then we have some random error around this forecast. Okay? Then this error is normal distributed to the first approximation. Okay? So even though the normal distribution is not a very good model for the W itself, it's often not quite a bad model for the error. Okay? For the error. Because if you look at this, right? So this is my forecast, W hat, my estimate. Then the error is sort of, right? So not bad to model the error something like this. Okay, it's centered as a forecast, which makes perfect sense. If you're going to forecast, now your error should be, right? It should be centered. That's right. So it should not be, too high to one side to the other side. We're talking the error. So then the error will decay, right? Where as you go further and further away from the forecast, we're more and more sure it's unlikely to fall very far apart. The value will be very far away. Okay. So to model this kind of error is still, sometimes reasonable, at least when you're doing the first approximation, or let's say you're doing some, some back of the envelope calculations to model as a normal distributed. to model the error as normally distributed. So that's not a bad approximation. Okay. So if you read a lot of papers, for in renewable forecasting, both for wind and in renewables, both for wind and solar, if you see something like, oh, we assume it is normally distributed or assume it's Gaussian, sometimes you should dismiss this, because if they assume the entire wind generation as normally distributed, then it's probably a bad assumption. Okay, it's not normal. However, if they assume the air is normally distributed, then the conclusion may not be too bad. Okay, then the conclusion may still be okay, right? So this is another sort of thinking about randomness as thinking about the randomness in the entire thing, the W itself, versus the randomness in the forecasting error. Okay, so as operators, you often need to think about both, right? So if you're building a wind turbine, you need to think about, what is the possible range of power can output. If I operate this thing over a year, I need to know the shape of the distribution. That's probably not a Gaussian. However, if I operate this day to day, if I need to know what to do with this thing for tomorrow, then I only need to probably worry about the air. I have a forecast, I need to worry about the forecast air. The air is, modeling as Gaussian is not too bad, right? It's not the worst thing you can do. Okay, so you need to be sort of careful with thinking about this kind of randomness probability. Okay. All right, so we'll end here today. Next class, we'll look at the other distributions you may not be so familiar with, but they turn out to be a better model to use, at least for the entire wind generation, for this doubling, for the full doubling. Okay. And then this week's homework is out. Not too much probability on it, but the next homework, after we cover the other two distributions, we'll go a lot more into probability in the homework. We'll talk about forecast error versus the entire distribution, things like that. Okay. So take a look at this week's homework. It's out now. Due next Wednesday. Right? Thanks, guys.
Thank you.